Good morning, Thermo students. Welcome to thermodynamics. Trying to get this thing to turn on here. Wonder what the secret is. Need to pin this thing. Stuart, how are you?
I'm doing pretty good, but I still can't find the test on the on Blackboard.
Well, I put it on last night. Should be on there. I extended the time. You're not having any luck at all? When is the last time? When's the last time you looked?
Yesterday afternoon, probably.
Oh, it was last night. Look again, okay?
Yeah. Oh, I did look this morning. I don't know why there's not. Yeah, I don't see it at all. I looked this morning as well.
You don't see it this morning.
Are you guys referring to the test?
Yeah, we're referring to the test. Can somebody help us?
Yeah, I'm not seeing it either.
Okay. Let me go confer with my IT guru. Just one tiny minute. That's kind of strange. Just now. I think he's off from the fire department that Tuesday. But I guess.
Need to keep our doors locked and no garage doors open because somebody got shot cops at either 21st and Memorial or 21st and I-44 is your different addresses given, and they haven't found it yet.
Oh, great. Just great. I'm back. Hello, everyone. Let's see who's with me here. We've got Stuart, Cameron. Both of you guys had trouble finding your test, and my IT person has gone off to. That's my daughter. She's gone off to her job. We attempted to put that, extend that time for you guys last night. And I don't know. We'll figure it out. We will figure it out. So it's just the three of us right now, Stuart, Cameron, and me. But it's not class time yet. It's just 8:25.
I have a question, Mr. Griffin.
Yeah, go ahead.
Since I missed last Thursday,
Uh-huh.
I ended up not doing, I think it was assignment number 4.
Yeah.
And I was wondering if you could give me those numbers so I could turn it in late.
Yeah, let's do that. Now, who am I talking to?
Cameron?
Okay, Cameron, just a minute. Let me snoop around here and see. Let's see, Cameron. Yeah, it looks like now the last one we did was chapter 4, number 59. Can you write that down, Cameron?
Yeah.
And chapter 4, 108E. Write that down. But Cameron,
108E.
yeah, 108E. But Cameron, I'm also missing 430 and 426 from you.
Okay.
Did you do those?
I can look in my pile here and see if I have it.
Yeah, see if you have them. And I don't know what happened with the test, but obviously we've had some problem because there's several of you that had trouble. Some of you successfully got the test to me and I graded it and all, but some of you didn't. And I have a feeling it's not exactly your fault. So we'll figure it out somehow.
Yeah, I guess I don't have those other ones you were.
Yeah, well, I
What
don't
is
know.
that assignment, I guess? I didn't
They're gonna,
realize.
they're going to be late, but
That's better
maybe
than nothing.
maybe I'll be nice. Turn it in anyhow.
You want me to just email those to you?
I don't know of any other way to do it.
Okay.
We'll do it that way.
What were the 2 problems for the second one?
Did
It
I
was
say
like 430 and
430 and 426? Is that what I said? Yeah, 430 and 4-26.
okay, thank you.
Yeah, you're always welcome. Well, we could it's almost time for class. We could get started. Was there any other comments or questions before we launch into our exciting topics for today? Well, it might just be the 3 of us. I don't know. Let's see if anybody else showed up here. How come I'm so much in this picture? That's kind of weird. Hey, we've got some more customers. Megan showed up. We've got Megan now. That's good. Let me ask you, anybody that wants to answer, are you guys able to pull up the lectures on YouTube?
Yes.
Good. Good, excellent. Okay, well, I guess let's get started then. And trying to get rid of this stuff here. Let's see. Okay, now the topics, we've got a whole bunch of stuff to do today and not very much time to do it in. But the first topic is the inequality of Clausius. I think that's how you spell Clausius, sort of like Santa Clausius. And it goes like this. And you'll find it in the tail end of chapter 6. It's actually on page 167 in my book. And I've told you before, but I wonder if you remember what this little circle stands for. I'll ask somebody. Well, Cameron, I just talked to Cameron. Cameron, what does that little circle stand for, Cameron?
I do not know.
Well, that's okay. It stands for a cycle. If you have a cycle, like on your PV graph, where you go from 1 to 2, but you don't quit, you keep going maybe from 2 to 3, and then you go from 3 back to 1. If you come back to where you started, you have gone in a cycle. And if you have a cycle, Clausius, I forget his first name, but he examined hundreds of heat engines, well, dozens, let's say. And he took the heat transfer and the temperature at which that heat transfer took place. See, heat transfer always takes place across a boundary. And he added up all of the heat transfers and divided by the temperatures at which the heat transfers took place across the boundary for a cycle, and they were always less than or equal to 0. And he came up with his law there. It was an experimental law and observation. It just you observe something like you drop a rock 100 times and it falls down to the ground, and so you make a law saying, hey, if I drop a rock, it's going to fall to the ground. That's kind of like what Clausius did with his inequality. But what we do is we break this up into 2 separate expressions here. We break it up like this, where it's equal to 0, and then we break it up like this, where, because see, you know what this sign means. It means less than or equal to. So you could put an or in between these statements here, and it's either equal to 0 or it's less than 0. And what Clausius came up with is, if it's equal to 0, then all the processes in your cycle are considered to be reversible. In fact, you could put a little symbol there, REV, for reversible. Now, if you have any irreversibilities, how do you spell irreversible? Well, it looks pretty good. Yeah, irreversible. If you have any irreversibilities, see, a big factor is friction. If you got any friction, your cycle won't come back to the same place that you had it. And if you have any irreversibilities, it's kind of like I explained, if you drop an egg, go in the kitchen, drop an egg on the kitchen floor, and that process is irreversible. You're not going to get that yolk back in the egg, and the shell's not going to be nice and oval anymore because it's broken and spattered all over the kitchen floor. You've got irreversibilities. If you do, then that's what you have. And then I forget whether it was Clausius or who got to looking at this one and said, if you have this thing here that adds up to 0 in a cycle, that thing has got to be a property. Now let me go through with you on what I mean. See, if you took and added up all the changes in pressure for a cycle, and if you came back to where you started, you'd have the same pressure that you started with, because pressure is a property. If you took all of the changes in specific volume and added it up in a cycle, you'd come back to where you started. Now these things are true whether you have reversible or irreversible, doesn't matter. If you had a cycle and you took all the changes in temperature for your cycle and you added them up, you'll get 0. Maybe you don't understand. Let me give you an idea here. Suppose you started off with your T1 was 20 degrees Celsius. And then you went T2, you got hotter and you went 80 degrees Celsius. And then T3, you cooled off to 50 degrees Celsius. And then you came back to T1 and you did a cycle. You went from T1 to T2 to T3 back to T1. Okay, well here, let's write the changes in temperature. From going from 1 to 2, the change in temperature from 1 to 2 is plus 60. The change in temperature from 2 to 3 is minus 30. And the change in temperature from 3 back to 1, because we're going to do a cycle, is, well, that's minus 30 also. Now, if you add all those temperature changes up, you don't really need to integrate there. You could just go the sum of all the changes in temperature. You get 0, because look, 60 and you add minus 30 and you add minus 30 and you total them all up and you get 0. And that's true for any property, temperature, specific volume. And this thing here, some smart person looked at this and said, hey, you know what? This thing here has got to be a property, and they gave it a name. And they said, well, let's just call that delta S. Delta S is the integral, but it's supposed to be a reversible process. Yeah, it has to be a reversible process. And if you have a reversible process, they call this the change in entropy. If you like little letters, they can write it like this. Need little letters. There we go. Now you notice I wrote that as delta S, but I could write it as ds, because you can write properties with exact differentials. Because you know what ds means? It means S2 minus S1 is what it means, where they're very close in limit as you take a derivative. And so in small letters, you could write this as delta little s is equal to, but you can't write this delta Q thing as an exact differential, because Q Q itself is not a property. See, properties don't depend on the path you take. Properties do not depend on the path you take, but heat transfer does. What's really weird about this thing, this is the definition, make it 3 lines there. This is the definition of entropy, actually. What makes it kind of weird is you got 2 things here. One of them is a property. Temperature is a property, but heat transfer is not. Heat transfer depends on the path that you take. It depends on the history of how you arrived at the value of your heat transfer. It is not strictly dependent on your starting and ending points. It depends on the path between the starting and ending points. It's just like work. See, work is not a property either. Let me refresh your memory here. I need a little room here. Need a little room. See, work, we'll use a little w. Work is the integral of P dV. And if you plotted that up, you guys all know if you had a process that you went from 1 to 2, there's 1, there's 2, there's your process. Well, see, your work per mass is the area under your PV diagram. But now if you took a different path, say you went from 1 to 2 this way, well, the change in temperature would be the same. It doesn't matter which path you take for the change in temperature, but the amount of work you do is different. Because see, the work under this, can you see that the work under that path is smaller than the work under this path here? Or if you took a path, say, like that, you'd get more work per mass on that path and less work. See, work is not a property, but temperature is. The change in specific volume is the same from 1 to 2. It doesn't matter what path you take. See, here's V2 here, and here's V1. And it doesn't matter whether you go from 1 to 2 here or from 1 to 2 here. It's the same because specific volume is a property. Properties don't depend on the path. And what's really weird is entropy is made up of something that is a property and something that is not a property. But if you have a reversible process, then this is the definition of what entropy is. Okay, well, great. Well, let's show you an example, so maybe this will make a little more sense. Any questions so far? And we will figure out that that exam. Put an extension on it last night. I don't know why it didn't seem to take. So maybe we can figure it out, guys and gals. We'll see. Okay, let's do an example. Suppose you boil some water. In fact, there's a problem in your book. Let's see if I can find it. We'll do a problem in your book. Let's see. This is problem. Shop around here. Sorry, I got lost here. Totally organized. Might have to make up my own problem if I can't find this one. Let me look in chapter 6 here just a minute. Okay. What I wanted to do was just boil some water. Simple problem. Boil some water. Yeah, but where the heck is it? Okay. Well, I can't find it. I hate that. Well, we'll make up our own problem. That's okay. We'll just make up our own problem. We're going to take some water. We'll do this on a PV diagram. And we're going to go from 1 to 2. We're just going to go straight across here. And we're going to boil some water from 1 to 2. There you go. And we're going to do it with an isobar. We're going to take some H2O. Let's say it's at maybe 200 degrees Celsius. And we're going to have an isobaric process from saturated liquid. See, that's what that is. That's saturated liquid. And this is saturated vapor. We're going to go from saturated liquid to saturated vapor. And what we want to do is we want to find some things like, for instance, the change in specific volume. That'd be interesting. How about the change in, I don't know, specific enthalpy? That'd be fun to do. How about the change in temperature? We could do the change in pressure. But what we're really after here is the heat transfer. Oh, I'm running out of space here. The amount of work done, and most importantly, the change in specific entropy. Now, see, they have entropies in the tables. I think you'll understand the tables better here in just a minute. But let's write down some of these things. Now, the change in specific volume, go to the back and find the tables here with me. And look up 200 Celsius. 200 Celsius. Okay, I found 200. There it is. I found 200 Celsius. Well, the change in specific volume is 0.12620 cubic meters per kilogram. I wonder what that is. It's my phone. It's one of those warning things that thunderstorms. Oh, okay, here it is. What it says is 2 officers were shot by suspect David Ware, who is armed and dangerous. Officers were shot at 3:30 a.m. near 8900 East 21st Street. The subject was wearing a faded red shirt, black shorts, and a black baseball cap. Call 911 if spotted. We live in a very sad and dangerous world. Okay, now Delta H. Hey, we could get that. Just find 200 Celsius for me. And I'm going to write down the Delta H, and it is 852.43. I need somebody out there to look in their tables and find those for me and say, uh-huh. Now you got to remember now what I'm doing here is actually VFG, because we're going from VG, well, we're going from VF to VG, and the difference is VFG. And here, this would be little HFG. I need to hear somebody say, uh-huh, they found those. I don't guess anybody's found them.
That's what I'm finding.
Yeah, good. Now, who was that? Was that my friend Cameron again?
That was Stewart.
Stuart, I'm going to ask you another question. What is the change in temperature going from state 1 to state 2? If you boil water, what happens to the temperature while it's boiling, Stuart? Earth calling Stuart. Come in, Stuart.
What was the question again?
The question is, what is the change in temperature going from state 1 to state 2? You're boiling water and you're boiling it at 200 Celsius. So what is the change in temperature when you boil water at 200 Celsius from state 1 to state 2? What's the change in temperature?
I'm not sure.
That's okay. Did you know, Stuart, that when you boil water, the temperature doesn't change? Like it's 212 Fahrenheit when you start boiling, and after a half an hour of boiling, guess what? It's still 212 Fahrenheit. Boiling is isothermal and isobaric. Did you know that, Stuart?
I mean, that makes sense.
Yeah, it does make sense. Now, Stuart, what is I'm picking on Stuart right now. Stuart, what is the change in pressure going from state 1 to state 2?
0.
Yeah, good going. Actually, we never wrote down the pressure, but I have it here in my book. According to this, it is 1553.8 kilopascals. That's what the book says the pressure is when you're at 200 Celsius, and it stays the same because it's an isobaric process. And now, I'm still picking on Stuart. Stuart, do you remember how to do the heat transfer per mass going from 1 to 2? You can just say, I don't remember. If you don't, it's okay.
I should remember.
You should. You're right. You should. I'll give you a hint. It has something to do with specific enthalpy. The heat transfer in an isobaric process is equal to what, Stuart? He's just having trouble this morning. Well, we'll pick on somebody else then. Let's see. How about my friend Parker? Parker, glad that you showed up. We got some more students here. We got a bunch of students. Look at here. We definitely have for Parker.
Yep.
What's the heat transfer in an isobaric process?
I can't find it, and I don't remember.
That's why I keep asking you this stuff. If I keep bugging you about it, maybe it'll sink in. It's equal to the change in specific enthalpy. Parker, do you remember that now?
Yeah.
Now, I think I've warned you about this, though. This only works if it's an isobar. If it's not an isobar, it doesn't work. But we have an isobar. Look, that's an isobar. So this is equal to, in this case, HFG. So we can write down that the heat transfer is 852.43 kilojoules per kilogram. Now the work. I think I've taught you guys this, that the work is the area under your PV graph. I know I've taught you that. And in this case, it's just a rectangle. So you take the height and you multiply by the width. Well, let's do that. And need a little room here, though. Just a minute. Let me find some room here. The area of a rectangle is the height, which is, in this case, the height is actually 1553.8 kilopascals. And the width, well, the width is the delta V. That's the 0.1262 cubic meters per kilogram. This will give you the work per mass. Okay, and do that on your calculators, and I'm going to do it, and we'll see if we can agree on that. Well, I got an answer of 196. You could round it off to 1 kilojoules per kilogram. So we have the work per mass. Now, we already have the Q. We have our first law that says delta U is equal to Q minus W. We just figured the W. And we figured the Q, didn't we? We know both of them. So we can get the change in our specific internal energy by just subtracting. I think we could do it. See, this little w here is 196.1. So let's get that change in specific internal energy. I'm just going to subtract. We know these. I'm going to subtract them. Here goes. 852 minus 196. And I'm getting delta U is 656.3 kilojoules per kilogram. Okay. We never looked up delta U. Let's look it up. In the tables, delta U is, what is it, 200 Celsius? According to the tables, delta U is 1744.66. Am I on the wrong page or something? That's delta U. Yeah, there we go. Oh, wait a minute, something bad happened. That's not the same as that. I did something wrong. We're going to have to find out what it is here. Just a minute. There's the Q. Okay. And then we're going to subtract the W. No, I think I did that right. But see, delta U should be UFG. Okay, something very bad happened. And I don't know what it is right now. Did we do that work correctly? Did we take the pressure? I think that pressure is right. And did we take the change in specific volume? Did we get that right? Yeah, I think that's right. And when you multiply that, I think that's right. And so when you take the heat transfer per mass and subtract that, you should get the right answer. Okay, I do not know. I'm confused right now. I did something wrong. If any of you, okay, now here's the problem. I just found the problem. I wrote down, I got to have somebody out there correct me when I goof up. I wrote down HF. This is not HFG. It's not HFG. It's HF. This is a wrong number. I goofed up. You guys are going to have to help me. I'm getting the correct number in the tables for the change in specific enthalpy is 1940.75. Now somebody look in their tables and see if you can find that HFG of 1940.75. And I want to hear an uh-huh. You got to help me on this. You got to stay with me on this.
I found it.
Yay, good going. Okay, now if we take that delta H, then the heat transfer is equal to that delta H. This is the wrong number. See, I goofed up here. It's okay to goof up, but it's even better though to be able to find out what the heck you did wrong and fix it. Okay, now I've got my Q. Now we're going to put that Q in here where it's supposed to be. See, I had the wrong number in here. 1940.75. 1940. Oh, I'm running out of space here. I think I did that right. And so now we're going to get the work done, and it's not this. This is a screw up. Okay, well here we go. 1940.75 times the 0.1262. I'm getting 244.9 something. 244.9 something. And so it's not 196, it's 244.9 kilojoules per kilogram. I think maybe I got everything right so far. Okay. Now, when I take that when I take that Q and I subtract that correct value for work, let's see what we get. The Q was 1940.
Why did you change the pressure for to find the work?
The pressure was 1553. Oh, wait a minute. This is wrong. I'm so proud of you. Now, who was that just now?
That was Stuart.
Stuart, you get a honking thank you point over here in the corner. I wrote down the wrong pressure. It's 1553.8, thanks to Stuart. And we're going to get our work now. Here we go. 1553.8 times 0.12. You got to stay with me on this. I'm getting 196 kilojoules per kilogram for the work. 196. Okay. So delta U should be Q minus W. All right. Well, now the Q is 1940. I think we did that right. This is going to be wrong. The Q is going to be 1940.75 minus the work, which is 196. I wonder if I did that right. I get 1744 something, I'll round it off. 1745 for delta U. Hey, look at here. Actually, 1744. Things are looking up finally, guys. 0.8 is what I get. But now when I look up delta U in the tables, it says 1744 point, I don't know, round it off to 7. Hey, confirm. Look, it checks out. We did great. We've got a lot of stuff here. We got the little w, we got the little q, we got all this stuff. But what about the change in entropy? That's what I'm trying to talk to you about today, is the change in entropy. I'm talking about this stuff here. Well, according to that, it's the, here we go, this equation here, it's the integral, that's supposed to be an equal sign. It's the integral of all your heat transfers divided by your temperature at which it's transferred. Okay, well, let's do that. I need a little room here someplace. There's some room over here in this corner. Let's see, who's next? I think I'm going to pick on Megan next. Get nervous, Megan. We'll pick on you next. Okay. If you use this equation here and you want to find the change in specific entropy, it's I want to use this equation here. The temperature is constant, so you could pull it out. You could have 1 over the temperature and just call it Q, total Q. See, because if the temperature is constant, you can pull it out. You guys all took calculus. And what is the temperature? Well, you can't use Celsius, you have to use Kelvin. So it's 473, 15 guys, Kelvin. And see, we know what the Q is. The Q is the 1940.75 kilojoules per kilogram. So we can get our change in specific entropy. Here goes. We're plugging that in. We figured out what our Q was, and it checked out. 1940.75 divided by 473.15. You have to use Kelvin. Did you get 4.10 kilojoules per kilogram Kelvin. 4.10. Well, that's what I got. But see, we could have just looked that up in the tables. Delta S in this case should be SFG. Well, let's look up and see what SFG is at 200 Celsius. Go to your tables. Look up 200 degrees Celsius. And what does it say? Well, it says 4.1014 is what my tables say. Kilojoules per kilogram Kelvin. Now let's compare that with what we got. Well, it's the same thing. Look, 4.10, 4.10. You wonder where they got these entropy tables. They got them from doing this. Because you know all the other stuff. You know the little h's and the little v's and the pressures and the temperatures. So we figured the change in specific entropy the hard way, didn't we? I mean, that was really the hard way. We could have just looked this up in the table. Look, that's in the table. Now let's review now what how you use those tables. I'm going to erase all this unless somebody has a question. Nobody said anything. All right, I'm going to erase all this. If you have tables, well, you use the tables. Absolutely. We just did a sample problem there. We used our first law. We found the area of a rectangle. We found the change in specific entropy. We learned that entropy, the whole concept of entropy, is based on, I didn't spell inequality right. Somebody needs to help me in this class. That's not how you spell inequality, is it? I think I'm missing an A right in there. It's inequality. I missed an A. What I wrote was inequality. It's all based, the definition of entropy is based on Clausius inequality. Now, here's the way this works. It's the same old boring stuff that we've studied before. Haven't we studied little v? In the tables, little v is VF plus the quality times VFG. We've studied that. How about little u? Isn't little u UF plus quality UFG? It's the same deal. Little h is UF plus quality UFG. And these are all in the tables. And see, entropy is a property, just like specific volume is a property. These are properties. Specific internal energy is a property. Doesn't depend how you arrived at the value. And specific enthalpy is a property. And if you have tables, you just look them up. Okay, if you have tables. Well, if you don't have tables and if you have an ideal gas, that's a little different story. I need to show you the equations that you use for an ideal gas. So the topic right now, you understand about the tables and how to look stuff up in the tables. And I've told you what entropy is. I'm kind of sorry I erased that last thing because I wanted to show you one other thing. See this equation here? You can write that like this. And it has to be a reversible process for that to be true. Now what I did was, this is the differential form of that. This is the integrated form of that. See, if you integrate this, if you integrate both sides like that, you will get that, because that is the change in specific entropy. That's equal to the change in specific entropy. This is just the derivative form of this, and this is the integration form of that. It's sort of like it's sort of like 25. It's sort of like 3 plus 8 is 11, and 11 minus 3 is equal to 8. See, this is the addition, and this is a subtraction, but they're really saying the same thing, but this is addition, this is subtraction. This is differentiation, and this is integration. They're saying the same thing, but now watch this. Here's a clever little deal. dq is equal to t ds, isn't it? Can you get from here to here, students? And see, if you integrate if you integrated this, okay, now wait a minute, I'm getting myself confused now. Let's see. What you'll get is you get Q is equal to TDS if you integrated it, especially if you have constant temperature. Now this isn't always true, but if you had constant temperature, you could pull that T out. And we just did that problem, and we solved for the temperature, which was from memory, it wasn't it 473.15? Those of you that are taking excellent notes, that temperature was 473.15, wasn't it? Oh, yes, it was. And the delta S at 200, I still have my page open here. It was 4.1014 kilojoules per kilogram Kelvin. See that's the units of entropy. And if you multiply those, you'll get the heat transfer. And we got the heat transfer. Let me see what you get if you multiply these. 473 times 4.1014. I'm getting 1940.5 kilojoules per kilogram. Now, somebody that took notes of what we just did about 10 minutes ago, what did we get for the heat transfer? Anybody out there, speak up. What did we get for the heat? I'm hoping it was 1940, was it?
We had 1940.75.
Yay! Good deal. Now we got 1940. Thank you so much. Now, was that my friend? Oh, gee. That was my friend Megan, I think, right?
Yes.
Yeah, good going, Megan. We got 1940, 75. But now we didn't get it this way. We got it by doing this, Megan. We figured the W, that took a lot of work. Remember, it was a rectangle. And this here, I think we did it by going, no, we looked it up. Well, it was UFG is what it was. I almost made a mistake just then. I almost went C sub V delta T, but see, this is no good. Now, let me pick on Megan. So she's been very helpful. Megan, this UFG, what you got to do is you got to take U of G and you have to subtract U of F. You cannot do C sub V delta T to get this delta U. This is wrong. Megan, why is that wrong?
Isn't that for like an ideal gas or something?
That's exactly right. This here is for an ideal gas, and we don't have an ideal gas. In fact, we're boiling water, aren't we? We're starting off with 100% liquid water. And the question is, can you use an ideal gas equation on a jar of liquid water? Well, I hope not. That's why you can't do that. See, that's an ideal gas equation. We didn't have an ideal gas on that thing I just did. We were boiling water from liquid water to steam is what we were doing. And look, you get the same answer. You can get your heat transfer this way. Okay. Any comments or questions? Because what we need to talk about now is ideal gas. The next topic is we're going to talk about ideal gases now. What do you do if you have an ideal gas? But is there any comments or questions so far? I'm listening. Well, I found the problem that I meant to do with you a minute ago. I couldn't find it. We probably should do it to make sure you understand. But nobody's going to ask me anything. We do need to talk about ideal gases. That's for sure. But I want to make sure you guys understand this stuff. So let's do 625. It's on page P50 in my book. I guess P stands for page number, or no, problem. I bet that's what it stands for. Problem, page 50. It's the same thing we just did. It's talking about a constant pressure of 0.1 kilograms of saturated liquid water at 100 degrees Celsius And we're going to boil it until it becomes saturated vapor in a reversible process. They want the work, heat transfer. They want the work and the heat transfer. Now, what we're going to do is we're going to draw the PV diagram. Oops. Hopefully this will be very boring because we just did this. And if you did a PV diagram, you know, it goes like that. From saturated liquid to saturated vapor, it goes like this. There we go. There's state one, there's state two. Now, let's go to my friend. I'll start picking on you guys now. Let's see. How about my friend? I'm always picking on Stuart. But he was so nice to help me before. I'll give him a break. I'm going to pick on Roxana now. Roxana, I want to know what the pressure is here, Roxana. And we know the temperature, it's 100. Roxana, look in your book and see if you can find what the pressure is. I'm trying to find it. What's the pressure, Roxana? Kind of hard because you have to do it on your phone, don't you?
Yeah, I'm looking right now.
It's kind of hard to find, but I know you can do it.
Is it 101.3?
Very good. Proud of you. 101.3. Very good. 101.3 kilopascals. Now, we can do a shortcut here and get the heat transfer. Since it's an isobaric process, we just did something like this. It's just equal to HFG. Roxana, do you still have that page there with the tables? Do you have the HFG, Roxana? Can you see what it is?
Yeah. 2257.03.
Good going. Good going. See, that's the heat transfer. Now, we could get the change in entropy per mass by just taking that Q and dividing it by the temperature. Well, the temperature it's got to be in Kelvin. It'd be 373, wouldn't it? So we've got this Q here. Go ahead and take that and divide by that, and let's see what we get. We can get our change in specific entropy by dividing that by that. Go for it. I'll pick on somebody else besides Roxana. But I got an answer. Now check me, make sure I get this right, because I can push the wrong buttons just like you guys. Anybody getting that? Anybody getting that? By the way, if you wonder what are we doing now, I'm working problem 625. It's in your book. And we just figured out the change in specific entropy, we think. But I need to hear an uh-huh.
Yeah, I got that.
Yay. But see, we could have got that real quick and easy by just looking up SFG. Now let's do that. Everybody go to your tables at 100, is it 100 Celsius? Yeah. And look up SFG. Well, guess what it says? It says 604. Well, it's a little different, but that let's don't have a heart attack. There we go. It's 6048. This is 6048. Now the units are kilojoules per kilogram. Kelvin. Uh-oh. Hey, somebody could have helped us here. This is wrong. There needs to be a Kelvin right here. Now, I want you guys to jump on me when I make a mistake. See, the units for specific entropy are kilojoules per kilogram Kelvin. Quit making me find my own mistakes. I need you guys to help me here. Well, we got the same answer both ways, but now they wanted some other stuff. Now I forgot what they wanted. Let me read it here. If you're kind of dozing off, we're doing 625, and they wanted work, heat. They want work and heat. That's what they want. Okay, well, let's see what we can do. How do you find the work? Well, how did we do it the last time? Oh, I remember. We took the area underneath the graph. Well, that's how you find the work. The little w. If you have little v's, it's little w. And that area is 101.3. Here, let's write it as kilojoules per kilogram. No. That's wrong. Kilopascal is kilonewtons per square meter is what it is. It's kilopascal. Times, you need the change in specific entropy. No, you need the change in specific volume. Okay, well, I don't know what that is, but my book does. It's 1.67 185 cubic meters per kilogram. Now, when you multiply these units, what you'll get is a kilonewton meters per kilogram. And you know what that is? That's a kilojoule per kilogram. Okay, well, let's do that. Let's see what we get here. Here we go. 101.3. 101.3. 1.67185. Okay. Did you get 169.4 kilojoules per kilogram? We got our work per mass. Yay. Well, so what? Well, what else did they want? I forget. Work and the heat transfer. We got the heat transfer. There it is. There's the work. Now we could check it by using the first law. Delta U is equal to Q minus W. And we have the Q and we have the W. So we could definitely do that. So let me do that. Here it goes. So there's the W, and we're going to subtract that from 2257. Well, here's what I'm getting for delta U, 2087.7 kilojoules per kilogram. Now that should equal UFG. Let's see if it does. See, this is a way of checking our work. If that's equal to 2087 back here in the tables, we must have done something right. Help me find that now. What do we want, 100 Celsius? Oh, there it is. And what's the UFG? I'm not getting that. Wait a minute, something bad happened. Did we do Q right? I think we did Q right. Yeah. On second thought, we didn't do Q right. This is not right. Oh, no, wait a minute. I'm on the wrong table. I'm looking at an ammonia table. That's a big problem. Now, let me get on the right table here just a minute. Okay, now what I'm trying to do is to look up, I think we did all that right. Trying to find UFG, but for water, not for ammonia. It'll be very helpful to get on the right table. Now, here's what they said. They said, running out of space here, but they said UFG is equal to 2087.6. Hey, that's pretty close to 2087.7, isn't it? I'm pretty happy about that. We checked that. And we got the heat transfer. By the way, is that heat transfer going in or out? Let me draw a red arrow here, and I'll ask one of my wonderful students here. There's going to be a heat transfer. It's either going in or out. Heat is either being transferred in or it's being transferred out. Now let me go to my friend Bear, Earth Calling Bear. Bear, you've got a 50-50 chance of getting this right. Is that heat transfer going into our water when we're boiling it, or is it going out of our water? What do you think, Bear? Unmute and tell the gang what you think.
Is it going out?
Bear, you had a 50-50 chance. Don't go to the casino. Stay away from there. It's going in. When you boil water, you have to turn on the fire. And there's a heat transfer into, and so you'd want to draw your arrow like this. There's your Q right there. I tried to make it red, but oops, let me get rid of this here. Stay away from the casino. Okay, well, we answered their questions, I think. Did we do all the questions? Find the work and the heat transfer. Did we find the change in entropy? Yeah, we did that too. There's the change in entropy right there. Good deal. Okay, well, I want to talk to you now. I need to talk to you about ideal gas stuff. That's the big item, but there's one other thing here before we go on, and that is TS diagrams. So I need some room here. Okay, well, let me say goodbye to all this stuff for a minute. Did anyone have a question before we talk about TS diagrams? All right, well, the topic right now, there's a whole bunch of stuff today. This chapter 6 is just full of fascinating, good stuff. But we're studying TS diagrams. Now, the PV diagrams we've been studying for a long time. PV diagrams. Haven't I told you that the secret to success in this class is being able to put your process on a PV diagram? And on your homework, I've been looking at some of your homework, and you guys do real good. You're real smart. You know how to do algebra, and I'm real proud of you, but you're not doing what I ask. I want you to draw a PV diagram and put a process on it. And I've told you this several times before, but let me tell you again. If there is a process, what I mean is you have a state 1, and you have a process, and you go to a state 2. Like on that example we just did, was we had a liquid water and we boiled it, and state 2 was steam. We went from one state to another state. If you have a process like that, then draw the process on a PV diagram. Now, I know I've told you that before, and I know I've done it. When I do problems for you, have you ever noticed I do a PV diagram? I've done 2 of them today already, I think. I always do it. I want you to do it. Now, if there is a process, then draw the process on a PV diagram. Now, what happens if you don't do that? What happens if you solve the problem and do a wonderful job and you don't do the PV diagram with the process? What happens? This is what happens. You don't get a 4. I'm all for giving you guys 4s, okay? But if you don't do it, and if you continue to not do it, this is what you're going to get. Now, you know what a 2 is? A 2 out of 4, it's a high F. And that's a lot of work for you guys to do. All that looking stuff up and multiplying things, all that hard work for a lousy high F. Why don't you just do what I ask? If there is a process, then draw the process on a PV diagram. Now, what we're going to do now is, and we're going to have to learn how to do a TS diagram. So draw the process on a TS diagram also. That won't hurt you any. So right now we're going to talk about TS diagrams. Okay. Well, that's the topic right now, TS diagrams. And I've told you this over and over, but I find that people don't listen to me. But if I keep telling you, maybe you will. Now here's what a TS diagram looks like. Now, if you're dealing with water, it's got a vapor dome. It's a little more symmetrical, though, than the PV diagram. The PV diagram, see the PV diagram, it's more like the Sierra Mountains in California. It's real steep there where it drops down to the desert at Owens Valley. But it's real gradual where it gradually goes down to Yosemite and then Fresno, and then it goes to the Central Valley of California. It's real gradual on this side. The TS diagram is more like, what is that volcano in Tokyo? Tokyo, it's somebody help me. What's that volcano there by Tokyo? Come on, help. Nobody's going to help me. I can't think of the name. It's got some snow on the top, but it's a perfect, very symmetrical. My mind's blank. I can't think of it, but we're talking about TS diagrams, and they have isotherms. The isotherms go like this. They're flat. And this would be the hot ones. And then this would be the cooler ones. So the isotherms are like that. Now it's the isobars that are kind of strange. I've got some blue here. I like my isobars in blue. The isobars come up here like this, and they're also flat in the middle because, see, boiling is isobaric, like we've just been talking about. But then the isobars do that. And this one here, the isobar comes up and then it's flat. And then it does, it goes like that. Now these are the high pressure isobars, high pressure. And there's a low pressure isobars. You see down here you have a specific entropy. The entropy is getting bigger going this way. Temperature is getting hotter going that way. And that's how the isobars look. Now it also has isocores. The isocores, they're kind of weird. They're actually steeper than the, it's kind of hard for me to draw, but I'll try. They're kind of like this here. They're a little bit steeper. That's an isocore. Do you remember what isocores are? It's when you have constant something, constant specific volume. See, the isocores are steeper than the isobars. What's weird about them is these are the smaller ones up here. So the smaller one, isocores are here. And then the bigger isocores are up there, but they're steeper. Here, let me write that for you. Isocores are steeper than the isobars on a TS diagram. Now that's what a TS diagram looks like on a real gas, like water or ammonia or one of the refrigerants. If you have an ideal gas situation, you don't have these vapor dumps. Here, I'll try to draw you one. There's room here. Here we go. We'll put a TS diagram down here. And if you have an ideal gas, then the isobars, well, the isotherms, they're the same. They just, here's the really hot ones. And then here's the cooler ones. Those are the isotherms. That was supposed to be horizontal. There we go. But the isobars, they're kind of weird. They go like this and this. And these are the high pressure isobars, and these are the low pressure isobars. And the isocores, well, we talked about the isocores. They're just a little bit steeper than the isobars. So there you have it. Now, you can also have isenthalps. See, on a TS diagram, you can have straight up and down lines. And what these are, those are isenthalps. Constant enthalpy. And of course, these would be the big ones. This would be little s, the high value of specific entropy. And these over here would be the lower value of specific entropy. So there you have it. We talked to you about TS diagrams a little bit, and we're going to try to draw some. That'd be fun. Okay, well, we're going to talk about ideal gas. That's the topic now, unless you have a comment or question. The topic now is going to be dealing with ideal gas stuff, but I need to work into it and show you some things first. But it's time for about an 8-minute break. I want you to go stretch for 8 minutes. And we'll come back, and we're going to shift now. I think pretty much everything we've done is with was water, wasn't it? But we're going to deal with things like air now, or maybe helium. So I'll see you in 8 minutes at 10 or a little tiny bit after 10 o'clock. Go stretch for a few minutes, and we'll be back. It's break time. Hello. Let me think. Let me think. It's okay. Welcome back, Thermo students. I wanted to, before we go on to that ideal gas stuff, I wanted to show you, we did this problem last time, I guess last Wednesday. It was a Carnot cycle. And today I was telling you about Clausius's inequality. And we broke it into two parts. And one part is if it's reversible, and one part was if it's irreversible. Well, I just wanted to show you that. See, this is a cycle. You go from 1 to 2. Wait a minute, somebody's calling me. Just a second. Hang on. Yeah. Oh, okay. Do you want me to tell them to try it later? Oh, okay. Let me ask them. Hey, wonderful Thermo students. I've got my my IT person on the line, and she thinks she's got that test fixed. I forget who it was. Spencer, Cameron, somebody else. look and see if you can pull that test up, you guys. Can you do that? She thinks she's got it on there now. They're gonna do it.
Yeah, I think so.
Hey, I heard somebody just say, yeah, I think so. Now, who was that? Was that Spencer?
No, that was Cameron.
Cameron, can you see it now?
Yes, I got the test pulled up here.
Hey, Cameron says yes. I don't know about my other buddies, but yeah, I bet everybody can see it now. Hey, thank you, IT person. Bye. Okay, we maybe have that fixed. Now, back to this. I just wanted to show you this. Last Wednesday, we had a Carnot cycle. And I want to show you that it was problem 549 is what it was. And I wanted to show you that Clausius's inequality works for that. Remember, Clausius inequality goes like this. If you have a reversible cycle, and we do, see, because by definition, a Carnot cycle is reversible. Okay, well, we're just going to plug in these numbers and see what we get. Here we go. Well, the heat transfer is 250, and that's positive. That's a positive 250. And the temperature is 600 Kelvin. 600 Kelvin. And this happens to be kilojoules per kilogram. And then, but see, this is an algebraic, you add them all up throughout the whole cycle. Going from 1 to 2, that's what we have. Now going from 2 to 3, it's 0, because there is no heat transfer on the adiabat going from 2 to 3. And then going from 3 to 4, it's minus 125 over the temperature at which that heat transfer takes place, which is 300 Kelvin. And then finally going from 4 to 1, we have another adiabat. See, going from 4 to 1 is an adiabat. There is no heat transfer. So you just have a 0 and you total these up. Can you tell algebra students that 250 over 600 minus 125 over 300 will give you 0? And that's what Clausius said if you have a reversible cycle. Now, if there's any irreversibilities, you don't get 0. It's less than 0. Remember? So there, I wanted to show you that. Now let me erase. I'm going to erase all that unless you had a question. Did anyone have a question? Well, I guess not. Oh, gee, I touched this thing and oh man, something bad happened. Let's see if I can get it back. The moral is never touch anything. I need to come up here and there. I think maybe I'm okay. Hey, I hate to touch that, but I need to touch it just a little bit up here, like that. There. And maybe okay. I better be careful. All right, let me erase all this, and we're going to talk about actually something called the Gibbs equations. We need to know what to do if you have an ideal gas. All right. If you have an ideal gas, you're not going to use the tables. You're not going to go look up UF and UFG and all that stuff and HF and HFG and SF and et cetera, et cetera. But these are called the Gibbs equations. That's just the name of them. They're named after a famous person named Gibbs. And this one here goes like this. They're also called the TDS equations. Now these equations work whether it's an ideal gas or whether it's a liquid or a solid or a saturated mixture, or they work for any old thing. And some people call them the Gibbs equations. Some people call them the TDS equations. And they have another name. I can't think of it right now. But I'll show you where they come from. They come from the first law. You all know and love the first law. And see, we have been working with this business of entropy. And how did that go? Yeah, we had an equation like that on the board. In fact, it's really a defining equation. You know, it's a definition. And so you can get the Q. You can get the Q by integrating, and it's just equal to TDS. So you could substitute that. And what you'd have is this here. Just from the definition of what entropy is, and see the work is equal to P dV. See, if you integrated it, what I should do is I should write this as, let me move it up a little bit. I hate to confuse you guys. You all know and love that first law written like that, but see, you can write the first law like this. And if you integrated this, this is what you'll get. And if you do a little algebra with this, here's what you'll have. No, wait a minute, that's supposed to be a du. There we go. Now I think I have it right. What you'll get is this here. And hey, that's the first Gibbs equation. I just did it. Ta-da, we have just arrived at the first Gibbs equation. And how do we get it? Well, we got it by writing the first law. That's the first law that we know and love. And well, we wrote it in differential form. I hope none of you are confused by the definite differential and the indefinite differential. You see, you can't have a definite differential on heat transfer because heat transfer is not a property. You don't have heat at state 1 and heat at state 2, and you don't subtract them to get a difference, because heat depends on the process from 1 to 2. It doesn't depend on the initial and final states. It depends on the process. Whereas other things that are properties like little u, big T, little s, big P, little v, those things are properties. They depend only on the state, on the state 1 and where state 2 is, not on the pathway between them. Doesn't matter about the pathway. I think I tried to explain that. Now to get to, we just did this one. Ta-da! We just did this one. Yay! Now to get this one, what you have to do is you have to write what enthalpy is. By definition, enthalpy is U plus PV. We all know that. I could wake you up out of a sound sleep. Let me get my water. I left it over here. I could wake you up out of a sound sleep and ask you for the definition of enthalpy. And you would say, Mr. Griffin, it's U plus PV. Because you got that down. That's a definition. Watch this. We're going to do a couple of little calculus or algebra tricks here. dH is equal to du plus pdv plus dp times v. Do you recognize I used the product rule for differentiation, didn't I? Yeah, you did, Mr. Griffin. Okay, now what I'm going to do is another algebra step here, and I'm going to write this du as dH minus pdv minus dp times little v. And I'm going to take that du and I'm going to stick it in right there. And here's what I'll get. I will get dH minus pdv minus dpv plus pdv. Oh, look at the pdv's go bye-bye. And what you're left with is TDS equals DH minus dP times little v, minus v times dP. Ta-da! And we just showed you the Gibbs equations. Any comments or questions from anyone about the Gibbs equations? Oh, okay. If you're happy, I'm happy. Now we can come up with stuff for ideal gas. Now, up till now, I haven't told you that this is only good for ideal gases. These Gibbs equations are good for anything. They don't have to be ideal gases. But we're going to take this bottom equation and we're going to play with it. I just need a little room here to work. And we're going to come up with some wonderful equations for ideal gases. we're going to assume that you have an ideal gas. Okay. And you're going to have an ideal gas, so what? Well, follow me, see if you can follow this algebra. I'm going to divide everything through by T. See if you can get to here with me. And if it's an ideal gas, I could write that as C sub P dt. I'm dividing through by T. Can you get from here to here, thermo students? Can you make it? And I need an Unmute somebody and say Nobody's going to do it for me.
Yeah.
Yeah, I heard a yeah. Good going. Yeah. Now let me show you something. If you have an ideal gas, then PV is equal to RT, and V over T is equal to P over R. I bet you can get from here to here. I know you can. So we can rewrite this. Watch this now. We're doing some algebra now. We're going to write that as P dP over R. No, I did that wrong. No, wait a minute. V over T is R. I did it backwards. I caught my own mistake there. I found it. It's P. It's R. I got that upside down. It's R over P, isn't it? R over P. Now I think that's right. Stare at that and see if you agree with that. Okay, almost done, and we're going to have a lovely equation. Almost done. Here we go. We're going to do a little calculus trick. We're going to go meow, meow, meow. There we go. And of course, when you integrate that, you'll get delta S equals, see, we're not going to be able to go to the table and look up, say, for water, SFG anymore, because water, especially inside the vapor dome, is not an ideal gas. But you could use this on air or helium or a lot of other things that behave like ideal gases. And so here's what you got. Now, if this C sub P doesn't change much, you can pull it out and you'll get this here from T1 to T2. And if you're going to go from P1 to P2 on this one here, you get R natural log P2 over P1. So this is a very useful ideal gas. It's only good for ideal gases. In fact, whenever you see, hey, look, see that R right there? If you ever see an R in an equation, it should tip you off. Hey, wait a minute. That's the ideal gas constant, isn't it? That's that R thing. Look, that's that R thing in the ideal gas. You know what? This equation's only good for ideal gases. Of course, if you see C sub P, that should tell you the same thing. C sub P is only good for ideal gases. Okay, well, great. We got a lovely equation there. Now, I got that by taking this equation here and playing with it. I took that equation there and I divided it by T, And I did some calculus and some algebra, and by Jove, I got that. I could have taken this equation here and come up with a lovely equation that goes like this. I'm going to spare you the details. But here's what it looks like. That's almost as important, but not quite. I think this one here is even more useful than this one. Wait a minute, that needs to be a delta S. I'll get it right in a minute. There you go. See that equation there? That's an ideal gas equation. Yeah. Wait a minute. No. There, now I think I have it right. See this? These are both wonderful equations for the change in specific entropy. They're both good. Now that you have that, I could talk about that more. Let me tell you one last thing. You see this thing here? They have a special name for that. They call that an ideal gas integral. And they have tables of that in the back. And in the back of your book, they got these S0 with a little t there. And what that represents is the integral of c sub p dt over t. They've actually integrated it. What they've done is they've integrated it from a reference temperature. Some reference, it doesn't really matter, to some temperature. So like if you wanted to get, that's enough for now. I'll just tell you that. We'll work a problem. But you'll see these in the back of your book. See, if this was T2, then you'd have a T2 here. If it was T1, you'd have a T1 there. They're called ideal gas integrals, and they have them. Well, let me see if I can find some of them. I'm going to flip to the back of the book here, to the tables, and see if I can see any of those little S0 things. I don't see any. Oh, there's some. I found some for air. Found some for air there. A whole bunch of them. I wonder if there's any others. Oh yeah, they're all over the place. They've integrated. Okay, so now we know. So we've got those equations for the change in entropy. Well, it's time now. Oh gee. When do we get out of here? Let's see, we start at 8:30, 9:30. Hey, we've got 50 minutes left. I need to give you the second law of thermodynamics is what I need to do. We've got these equations. Let me make some room here. And the topic now is the second law of thermodynamics. I need some room here. There's just so much stuff today, kind of an overload. But did any of you have a comment or question before we discuss the second law of thermodynamics? Anybody? Comment or question? Well, nobody said anything. I wonder if anybody's listening. Let me see if there's still some wonderful. Yeah, we got a whole slew of wonderful students. You know, I never took roll. Not that it's important. It's just nice for me to know that some of you care enough to tune in. But see, if you can't, you could always watch it on YouTube, huh? Now today's the 29th of June. And we've got Bear, Cameron, and Megan. Let me mark them down. Let's see, Bear, and Cameron and Megan. Okay. Bear, Cameron, and Megan. All right. And we have Parker, Roxanne, and Stuart. Where's Stuart? Yeah, there he is. Roxana. Did I say Parker? I think so. And Aubrey's on there too. I'm pretty sure. I'm not sure. Let me double check. If Aubrey, are you there? Yeah, Aubrey's there. Yeah, absolutely. Aubrey's there. Let me find her. Yeah, here's Aubrey. Okay, good. What about my friend Spencer? He's not there? Spencer, where are you? Maybe he can watch the YouTube. And my friend Mohammed, he's not on there either. Well, okay. Now what were we going to do? Oh, second law. Actually, they give you an English version of the second law in chapter 5. I don't know if you read about that, but let me just mention that real quick. See, they have a sentence, an English sentence. Is that how you spell sentence? S-E-N-T-E-N-C-E? Looks good to me. I think it's right. And in chapter 5, they have a version of the second law of thermodynamics. And I'll tell you where it is. It's on page 149. They have a Kelvin Planck version. And they also have a Clausius version. We talked about Clausius here a little while ago. Now, the Kelvin Planck version, what it says is, if you have a heat engine, remember those heat engines where you have what do they call that? The clockwise cycle, and you have a high temperature and a low temperature, and you have a QH dot and a QL dot and a W dot in a high temperature. That's what a heat engine looks like. And you always have the lower temperature. It's called a heat sink. You have a heat source and a heat sink, and you got yourself a power cycle. Well, the Kelvin Planck statement says, if you got a heat engine cycle, you got to have this heat sink. You can't have no heat sink. There'll be you're going to have a high temperature, and you're going to have some work. But see, if you could have a heat engine like that with no, they said the second law says it's impossible. This is impossible. You can't have that. It's impossible to have a heat engine with no heat sink. Because see, if you did, you know what your efficiency would be? Your efficiency would be 100%. And there is another way of expressing this is there is no such thing as 100% efficient power cycle. They do not exist. That's kind of weird, but that's the way they say it. You can read it for yourself. It's on page 149. Now, the Clausius version of the second law, it deals with the refrigeration cycles. Now, remember, they go counterclockwise, and they go like this, and you have a high temperature, and you have a low temperature. But now the power has to go into the cycle. You have to provide power that goes into the refrigeration cycle, or it doesn't work so good. Try unplugging your refrigerator or freezer and see how cold it'll stay for a couple of days. It won't. And what the Clausius version of the second law says is it's impossible to have a refrigeration cycle that you don't plug in. You just have a hot and a cold, and that's it. In other words, they've got heat transfer from the cold to the hot, and that Mother Nature doesn't like that. Mother Nature says the heat transfer always occurs in nature from the hot to cold, not from the cold to the hot, and this is impossible. So if you have a refrigeration cycle that works without plugging it in, let me know. We could make some money, but it violates the second law of thermodynamics. Now that's in chapter 5. Now chapter 6, they get to the second law of thermodynamics, but they write it with algebra. They've got some algebra they're doing it with. Let's go through that and show you that, and we'll have our second law. Any comments or questions before we tackle the algebraic version of the second law of thermodynamics? See, you could put the first law of thermodynamics in a sentence form. You certainly could. We have the equations for the first law of thermodynamics. I could wake you up out of a sound sleep and you could write them down for me. But if you were to write out the first law, it would go like this. If you just wanted to write a paragraph or a sentence, it would be the energy, I'm making this up, but I think it's okay. The energy of a system depends on three things. Heat transfer. Because see, if you have a heat transfer into a system, it will increase its energy. That makes sense. Work. If work is done on a system, it will increase its energy. That makes sense. And mass flow. See, there's energy in mass. And if you're pumping mass into a system, you're pumping energy into the system because mass has energy. And so the energy of a system depends on three things: the heat transfer, work, and mass flow. Ta-da! I've just written the first law for you in English words, all right? But now what we want is a second law with algebraic symbols. That's what we're after. Second law of thermodynamics. And they explain this on page, let's see if I can find it here in your book. We talked about TS diagrams. You could you could read your book. They tell you about TS diagrams. Now this is on page 191. And what they've done is they've done a big PV diagram. And they've gone from 1 to 2, state 1. And here's state 2. And they did a reversible process from 1 to 2. There you go. Reversible process A. And then from 2 to 1, back to 1. When you got a cycle, we'll call that reversible process B. Now, according to Clausius's inequality, we have a cycle. And if these are both reversible, if they're both reversible, then if you made the integral of the dq over t total for the cycle, it would equal the dq over t for process A plus the dq over t for process B, and you would get 0. Why? Well, because Clausius said so. He said that if this is reversible, then the total for your cycle is 0. Then they did something kind of cute. They said, well, let's say we go up, instead of going up from 1 to 2 on a reversible, let's go up from 1 to 2 on an irreversible. We'll call this process C. And see, process C is irreversible. And so the integration of that for your cycle, you can't call the total cycle reversible because it's got some irreversibilities. Because see, we're going to go up C and then we're going to come back B. And we'll write it. Here we go. We'll go up C and then we'll come back B. I don't know if this is making any sense. It probably isn't. But Clausius says that that's going to be less than 0 because we have process C, which is irreversible. See, this one here, process B, is reversible. But process C is irreversible. Now we're going to do a little algebra trick. We're going to subtract this equation from that equation. Now, when you take this and you subtract that, they're both the same. So they go bye-bye. And if you take this and you subtract that, here's what you get. If you don't understand what I'm doing, you could read your book. It's on page 191. Now, when you subtract this, we're subtracting. And if you'll humor me, we'll be almost done and we'll have our second law of thermodynamics. Now that's an irreversible process. Now when you subtract those, you're going to have a 0 subtracting something that's less than 0. Well, when you subtract something that's less than 0, it becomes positive. You guys know that from algebra. So you have that equation there. Now see if you can follow this. We're going to write this, just doing a little algebra step here. Now keep in mind, this is reversible here, but we're going to put this over on the right-hand side of the equation, and it will say this. That's process C, and it's irreversible. And the thing is, if you do that, there's going to be a greater than. There's my greater than sign, because I put this over here, see. I don't know if you made it to there, but what they decided to do was, they don't like this inequality, so they said, this is bigger than that. So I tell you what let's do. Let's make that equal, and the way we'll make it equal is we'll just add some small positive quantity to the right. And there's some room up here. I'll do it up here. I just need some room up here. Come up here and write this. That was process A, and it's reversible. But instead of having it bigger than, we're going to set it equal to this. And we're going to add, some small positive quantity. I don't know what, but it'll have to be positive because that's bigger than that. They gave it a name. They called it, well, I'll show you what they called it. But this here, by definition, is equal to the change in entropy, by definition, from 1 to 2. We're going from T1 to T2. And you could put by definition, that's the change. That's what entropy is. We talked about that a little bit earlier. And the change in entropy, since it's a property, is the same no matter what process you take. So it's the same as A here. You could put an A right there instead of a C, because remember, the change in temperature is the same between 1 and 2, no matter what path you take. The change in entropy is the same between 1 and 2, no matter what path you take, because entropy is a property. So you could put an A right there, and let's put an A right there, and let's give this a name. Let's call it generated entropy. So now we have our first law. Maybe you didn't understand that, but here it goes. This is our second law, I mean. Our second law says this. Second law of thermodynamics says this. The change in entropy between state 1 and state 2 is equal to this term here. Okay, now wait a minute, I got lost. That's supposed to be a C. That's supposed to be a C. Did I do that right? Now let me think. I hope I'm not lying to you. Yeah, I think that's right. Yeah, that's right. The change in entropy between 1 and 2 is equal to this term here. Now remember, this is irreversible because it's on an irreversible. It's got some irreversibility. You're looking at the second law of thermodynamics. Now this thing here is called the generated specific entropy, and there's 3 things that can happen. Let me make you some. Hey, look, if you didn't understand that, read your book. There's 3 things that can happen. The generated entropy can be 0, And if that's the case, you have a reversible process. The generated entropy can be bigger than 0. And if that's the case, you have an irreversible process. Or the third possibility is the generated entropy could be less than 0. If that happens, you have an impossible process. As far as we know, that's never happened. It violates the second law of thermodynamics. So there you have it. Now we have our second law with algebraic symbols. Isn't that nice? It's not in an English sentence, it's in algebraic symbols. And now it's time to work a problem. We have a half hour. Let's do a problem. Here goes. I want to do problem 691. But before I do problem 691, are there any comments or questions? You guys are awfully quiet. That's kind of disturbing. Nobody asked me anything. Okay, well, here goes. We're going to do problem 691. And maybe we can learn something from plugging in the numbers and solving it. Let me find it now. 691. Here goes. Argon. We're talking about argon. So let's go to the back and let's look up R and C sub P and C sub V. So go to the back with me and make sure I get these right. Trying to find argon now. And now we in English or SI here. See, we're going to do 691. Oh, this is SI, isn't it? Okay. I'm looking for argon. There it is. And now the R is 0.2081. Kilojoules, kilogram, Kelvin. Now what's the C sub P for argon? 0.520. Kilojoules per kilogram. Okay, what's the C sub V for argon? 0.312. 0.312. Now, just to check to make sure I got those right, I think I've shown you guys that R is supposed to equal C sub P minus C sub V. Put those in your calculator and let's see what you get. Let's see, 0.2081 minus 0.520. Oh yeah, that's pretty good. Well, now wait a minute. Let's see, 0.520 minus 0.312. Yeah. Well, I get 0.208 instead of 0.2081, but it's good, guys. It's one of those round off things. Now let me read my problem here. Argon in a light bulb. Why don't we draw it? It's a light bulb. Okay. There you go, light bulb. Argon. Here's state 1. And state 1 is 110 kilopascal, 90 Celsius. The light's turned off, so the argon cools to the ambient temperature of 20. Well, here, let's draw state 2 now. Here's state 2. And now it's going to be 20 degrees Celsius. I think we got a heat transfer going on here, don't you? When it cools off, it's hot. Guys, this thing's hot. It's bright. And then I think you got some heat transfer out. See, there's your Q. There's some heat transfer out. Cools off. Now it's 20 degrees Celsius. Then what? Let me keep reading here. Cools in. Just disregard the glass and find the specific entropy generation. Okay. See, back to the second law. The second law says the change in specific entropy is equal to it's equal to this. And that's what they want. That's what they want, right? Okay. Now, you got to know something about this temperature here. That's the temperature of the boundary. Well, see, the boundary is 20 degrees Celsius. Everywhere out here is 20 degrees Celsius. That's the room temperature of the light bulb. And when you turn the light off, the temperature of the air in the room is still 20 degrees Celsius. Now, it's true that you might be heating up a little bit of the air next to the bulb, but there's wind currents, and your room is huge, and so you're not really heating up the room much. When you turn on a light and you take the temperature of your room, come back hours later, is your room just, oh man, it's hot because I had that light on? No, it's pretty much the same. I guess theoretically, it might heat up a teeny tiny fraction of a degree Celsius, but you got to understand that this temperature is not the temperature inside the light bulb. The temperature inside the light bulb was 90 degrees Celsius inside. And now the temperature inside the light bulb is the same temperature outside the light bulb because it's been turned off. And after a while, put your hand on it. Yeah. Hey, it's room temperature because it's not on, right? It's been off for hours, and it goes back to room temperature. So you could write this. You could write that as the heat transfer divided by your room temperature, which is 293, plus your generated specific entropy. Now, we're going to get this delta S from that lovely equation that we came up with earlier. It goes like this. There's two of them. One of them goes like this. Why don't we use both of them? And the other one goes like this. I think we can use both of them. Now here's the game plan, guys. If we can figure out this change in specific entropy, we'll have to figure out that Q too, won't we? We'll have to figure out the change in the heat transfer. How are we going to do that? I don't know. We'll work on it. This is what they want. they want us to find the specific generated entropy in this process. See, there's a process from here to here. There's a process. Now, the question is, what kind of process? Now, let me give you some choices here. There's isobaric. There's isothermal. There's isochoric. There's polytropic. There's even other ones that there's thousands of processes. Now I'm going to go to one of my wonderful students here, and there's a process because we're changing states from 1 to 2. There's a process. You know what that means? That means we got to write a PV diagram and a TS diagram. Oh, we only have 19 minutes. But let me go to one of my excellent students here. Stuart, I'm always picking on Stuart, but he's a good sport. Stuart, you got 5 choices here. 1, 2, 3. What kind of process do you think we have between 1 and 2, Stuart? Stuart's thinking. Unmute. You got a 20% chance here. That's not very good at the casino. 1 out of 5. What do you think? Uh-oh. Might have lost Stuart.
Is it polytropic?
No, but thank you for rendering that. Actually, it's possible to assign that to a polytropic, but I probably shouldn't have given you that choice. I don't want to go into that. We'll take that one off the table here, Stuart. And we're going to go to my friend Roxana. Roxana, you got 4 choices now. You got 25% chance of getting this. What do you think it is, Roxana?
Is it, what does it say below isothermal?
Let me read that. Let's see. It says isochoric.
Is it that one?
Yes. Very good, Roxana. It's an isochoric. Roxana, what is an isochoric process? She did process of elimination. She knows.
Constant volume.
That's it. Good going. Proud of you. See this light bulb. I don't know if you ever looked at a light bulb, but they don't change their volume much. They don't get bigger. They come back a few hours. It's the same light bulb, same volume, okay? It's an isochoric process. All right, well, great. Of these 2 equations, I'd like to do both, but right now this one looks pretty easy because if V2 and V1 are the same, then you have the natural log of 1, which is 0. So this term here drops out, and we can get our delta S. It's equal to C sub V, which we know, natural log of T2 over T1. And we know all of that. Okay, let's do that. I need some room in here. That was kind of fun. We're going to get the change in specific entropy now. It's equal to C sub V, 0.312 kilojoules, kilogram Kelvin. Natural. Now, wait a minute. These have got to be in Kelvin or it doesn't work. So T2 is 20 degrees, which is 193 blah blah Kelvin, and T1 is Is it 363? I did that in my head. I'm not at all sure that's right. Let me double check that. You take 90 plus 273. Yeah, that's right. Okay, hey, now we're going to get our change in specific entropy. Here it comes. Help me do this. I need you guys to go along with this so that I don't make a mistake. 193.1.
Should T2 be 293?
Say that again. What about V2, V3? Say again.
Should T2 be 293?
I don't know. It might be. You have to take 90 plus 273, don't you? I think I did it right.
No, the one on the top.
Oh, yeah, wait a minute. Now, if you take 20 plus 273, you get, it's 293, isn't it? You're absolutely right. Now, was that Stuart? Who was that?
That was Parker.
Parker. What happened to the other wonderful students' thank you point? It got erased. That's too bad. But Parker, that one's yours. Proud of you. Parker's absolutely right. Now, do I have it right, Parker? The 293? I think so. Okay, let's do that. Here goes. I really appreciate you guys helping me out when I do that. 293. You have to divide by 363. Take the natural log. We have an answer. I'm getting negative 0.0668 kilojoules per kilogram Kelvin. And did you get that? I need an we're doing this equation right here, and we got delta S. Yeah, that's good. All right. Well, we're doing great. If we could only get the heat transfer, see this heat transfer? We know this. We got the delta S. We just solved it. It's this here. It's negative 0.066 something. If we could get this heat transfer, we could solve for this generated specific entropy. We could do it. Now, how are we going to get that heat transfer? I need a little room here someplace. There's some room here. We're doing, if you just woke up from a daydream, we're doing 691. It's a problem in your book. We're having lots of fun. And I need this little Q thing here, and here's how I'm going to get it. Now, I need to go to one of my wonderful students here. Hang on. And we'll go to Aubrey. Aubrey, I got a question for you. What's the work done in an isochoric process like that, Aubrey? Do you know? What's the work done?
0.
Yay, good going. Proud of you. It's 0. Because, see, there's no expansion. Remember, expansion work is positive. Compressive work is negative. But we're not expanding or compressing. We got 0 work here. So we can get our little q. Look here. Little q is going to equal C sub v delta t. Well, do we know C sub v? Yeah. And do we know delta t? Yeah. We'll do it. Help me get the little q. Here we go. Little q will be 0.312 times. Now, what is delta t when you go from 90 to 20? What is delta t? Here, I'll write it. It's 312. It's plus or minus 70, but which is it? Is it plus 70 or is it minus 70 when you go from 90 to 20? What do you think? What's the temperature when you cool off from 90 to 20? What's the change in temperature? Plus or minus?
Negative.
Yeah, it's negative. So the heat transfer, well, we knew it was negative. See, going out, heat transfer going out is negative. Heat transfer going in is positive. Okay, well, we can get our heat transfer. Here goes. I'm getting a negative 21.84 kilojoules per kilogram. So we have that. Hey, look, guys, see this equation? We just figured out what Q is. We have an equation now, and we know everything except the generated specific entropy. So let's get that. Here we go. I'm plugging in all this stuff. Now that Q is minus, so watch it, it's minus. Divide by 2, 93.15. Then you have to do some algebra. You have to take that and you have to do some algebra over here. Now what is delta S? Where is that? Oh, there it is. Yeah, there it is. 0.668. Well, I got an answer, guys, for little s GEN. Did you get 0.0077 kilojoules per kilogram Kelvin? And I'll wait till I hear two uh-huhs. I'm waiting. That's what I got. Is that what you got?
That's what I got.
Yay, yay. How about another uh-huh? I'm not going to get another uh-huh. Well, we have 6 minutes left. Now, what did I tell you about this? Let me make some room here. Let me make some room here. If the generated specific entropy is 0, then something happens. And if the generated specific entropy is bigger than 0, then something happens. And then if the generated specific entropy is less than 0, then something happens. So let me go to my friend Parker. Parker. Hey, Parker, was that your thank you point a little while ago?
Yeah.
Good going, proud of you. Now, Parker, if the generated specific entropy is 0, then what happens? What's the deal there?
If it equals 0, it's a reversible process.
That's it. That's it. That would be reversible. But we don't have that, Parker. We have a generated specific entropy that's, well, that's not 0. It's 0.0077. It's very small, but it's positive. So we have, what happens if it's positive, Parker? What do they call that?
It's an irreversible process.
That's right. It's irreversible. Now, Parker, if it's less than 0, what do they call that when it's less than 0?
An impossible.
It's impossible. It just cannot happen. It violates the second law of thermodynamics. Now, what would be fun is we found the change in entropy, remember? But we used this formula. Wouldn't it be fun to find it using this formula here? Well, yes, it would. Well, I bet we could. We know what C sub P is. Look, C sub P is sitting right here. We know that. We know T2 and T1. They have to be in Kelvin, but we know them. We know R. If we only knew P2 and P1, we could get it. Well, wait a minute, Auga. We know P1, don't we? You see it? Look at here. We know P1, don't we? They gave it to us. But we don't know P2. Oh gee, we only have 3 minutes left. If we could find P2, we could plug that in and we could check our work and make sure we got this right. I think we did get it right, but just for fun. I wonder how you would find P2. Does anyone have any ideas on how we could get the pressure at state 2? How would you get the pressure at state 2? How about, let me see who we got here. Uh-oh, I think some people left. Yeah, we're down to 4 students. Some of our wonderful students had to leave, but that's okay. They can always watch the whole thing over again. Let me show you how to get that P2, and then we're going to have to quit because we're running out of time. Make a little room over here. Here's how you could do it. P1 V1 is equal to R T1. Now we know P1, we know R, and we know T1. Hey, we could get V1, couldn't we? We could get V1, couldn't we? Yeah. Now look at here. P2, V2. But you know what? V2 is the same as V1, remember? Because it's an isochoric process. Once you solve for this V1 here, it's the same, P2 is the same, is equal to RT2. Now we know T2, we know R, we know V2 is the same as V1, and we could get P2. We could. If I had a little more time, I would love to do that. Then look at here. Then you'd have P2, and you could put that P2 in here, and you'd have everything here, and you could get your change in specific entropy from this equation. And it will be the same. It will equal minus 0.0668. Unfortunately, it's sad, but we're out of time. But didn't we have fun? And those of you that want to do that test, my IT person says that they're okay now. And of course, there's always homework to do. So do that homework for me too. All right, I'm going to put this on the little goodbye red button here. And when I push that, it's going to be bye-bye till Wednesday. Here's your last chance to say something. If you want to say anything now or never. 5, 4, 3, 2, 1. Blast off. We're ending the meeting.